Hello, this is Andrew with WMH Racing, and today in this video we are going to look at the internal resistance of a battery, and we are going to take and do a couple of different internal resistance tests. I'm then going to take one of those measurements and compare it to what the battery wizard does. The first test that we are going to do is what's called the AC impedance test. Now, this method of measuring the IR of the battery is very popular amongst commercial level battery manufacturers. And I'm not talking RC battery manufacturers. I mean, Duracell and whatnot, So this measurement uses, basically you apply a 1 kilohertz sine wave to the battery. So you apply an AC voltage to the battery, and you measure the resultant voltage drop across the terminals of the battery, and you divide that by the current in the circuit, and then you get the internal resistance. This is always a lower internal resistance than what's the other common method of the DC load test. Now, battery manufacturers like this method because of a couple of reasons. One reason, like I said, it displays a lower number, and that just looks better for them. But the main reason that battery manufacturers like this method is you're not actually putting a load on the battery. The state of charge of the battery doesn't matter. You don't have to make sure the battery is fully charged or not fully charged or what have you. The state of charge doesn't matter because it does not actually affect the DC voltage or the current capacity of the battery. Whereas a DC load test does, because you are putting a DC load. You're putting a load on the battery. All right, so the craziness I have set up here, I am going to create a 1 kilohertz sine wave using that meter. I am then going to come out the positive side, and that's going to go into the current port for this meter, and it's going to come out and into the positive terminal, oh good lord, positive terminal of the battery. Now, this current meter is in series for this circuit, so the current will pass through that current through the meter, and it will output on the screen how much current. From the return of the battery, we go through a ceramic capacitor and then back to the low potential, back to the function generator. Now, this ceramic capacitor is here to stop any DC signal from the battery getting back to the function generator. Since we're pushing an AC sine wave, we don't want that DC signal getting back to the battery or getting back to the function generator. We don't want to add on top that voltage. So this is capacitors in series will block a DC signal and allow AC to go through. They're really kind of cool like that. All right, anyway, what I'm going to do, I'm going to kind of focus. I kind of forgot the most important part. I got to read the voltage drop across the battery. Ha! All right, so this meter up in the upper left is actually going to read the voltage across the terminals. And we're going to have magic without actually reading anything, right? So there we go. Cross terminals. All right, there we go. Now, I am going to turn the output on. The output's going to start at 4 volts peak to peak, which is about 1.4 volts RMS. And you're going to notice that you're not going to get a reading on that top left meter. So I'm going to go ahead and crank it all the way up to 20 volts peak to peak, which is about 7 volts RMS. So we're going to be pushing 7 volts in this circuit, and we're going to measure the voltage drop across that battery. All right, let's turn this on. All right, so we have 0 volts reading, 0 millivolts reading on the battery, or on the meter, But we do have a current reading already of 22 milliamps. Now, we are measuring very, 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 very small voltages. And so not all meters, really honestly, not all meters can measure voltages this small. So we're going to crank this up. I'm going to notice that around 11 volts peak to peak, 12 volts peak to peak, we start getting readings, and we're going to go up to 20. All right, we are up there at 20 volts peak to peak, and we have a, now I want to show this to you. I'm going to get up on this and actually show this to you. That is 0.218219 millivolts AC. So that is, we're going to call that 218 microvolts. All right, now let's look at the current, and that's 112 milliamps. All right, I'm going to turn the output off, 218, 112. I'll turn the output off. I'm going to get my calculator here. 0.000218, 218 microvolts divided by 0.112, 112 milliamps. That equals 0.001946. That is 2 milliohms. 1.9 might as well be 2 milliohms. That is 2 milliohms AC impedance for the entire pack. Now we know that's pretty low, right? One, that pack is cool. It has not been charged at all today. So yeah, that's a very, very low reading for a pack. And the other thing to think about is, how does that actually apply to RC? What about that test do you think has anything to do with our application? I will leave you to ponder that. And I'm going to remove some of these wires so we can do other tests. Just going to unplug a bunch of things, get it out of the way. All right. Our next test is going to be with that. That is a DC load. Now you can see hooked to it, there are 4 wires. 2 wires are current carrying, and 2 wires are the voltage carrying wires. And this is to create what's known as a 4-wire measuring system. Like I said, there is no current on the voltage sensing wires. So we're going to plug that into our battery, and I am going to do a DC load test. Now, pressing these buttons and trying to measure everything and getting it right is very difficult. So what I have actually done is I have scripted I've scripted this in Python, so I can just do this. I plug everything in and run the script on my computer. So that is what we're going to do. Now up here on the computer, laptop, you can kind of see what's going on. So put the battery in view, maybe. All right, we got the battery. We got it plugged into the DC load. I guess I can show that, right? DC load plugged into battery. All right, we're good. All right. What I am going to do here, see if I can. So, and you see what we're actually doing. We're going to put a 40 amp load on this battery. 40 amp DC load is what we're actually going to put. You can come down here to the actual function when it actually does stuff. We're going to, let's see, up here, right there. I'm going to set the current level, enable the input. So we're going to write out to the DC load to set it at 40 amps, and then we're going to write it on. We have to sleep. We have to let the load happen, and then we query the voltage. Okay, and then we do a measurement to actually measure the voltage drop. So it does the voltage query first, then it's going to write the load, then it's going to sleep for a second, then it's going to query the voltage again, and then we're going to actually do a measurement, okay, and then turn off the load. During this process, we have to sleep for 1.25 seconds, and that's only because it takes a second for the signal to get to for the DC load to actually apply the load. I made this function as fast as I could get it and get repeatable measurements. Okay, so I'm going to take this script right here. So the output is going to output on this command line. I'm going to run the script. And 40 amp load. So we started with a voltage of 7.518. The voltage under load is 7.271. The current was 40 amps, and the calculated IR is 6.191 milliohms. All right, now why does this apply to RC cars? Well, the answer is when you pull the trigger or pull the throttle, or whatever you want to call it, push the sticks up, you send a signal to your ESC, which then opens the floodgates to the motor, and a voltage is applied to the tabs, to the phases of the motor. Now, that motor has resistors in it, which are a load. And the resistors create the voltage drop on the battery, and a massive amount of current goes through those coils. And is exactly what we're doing with the DC load. So the application is sound, right? This is a replication. All right, now let's take a look at what the Battery Wizard does. The Battery Wizard uses the exact same principle. Battery Wizard. Okay, we have a resistor bank that creates the DC load. The Battery Wizard has MOSFETs in it, and a 4-wire measurement system. So we can see the, sometimes you gotta get a good signal in there. Okay, so we can see that the voltage measurement right there is 7.521. The voltage, the battery has kicked back up a little bit from the 7.518. We're going to go to the menu. I'm going to go to the IR reading, right? And I'm going to hit check IR for the 200 amp check. And I get, let's see here, 6.07 milliohms on the 200 amp IR check, which is the check that I just did. So 6.07 milliohms compared to 6.191 milliohms. And I would say that is pretty damn close to a $1,200 DC load. All right, Battery Wizard puts load. This is our resistor box. This axle. This is like our motor. And then the Battery Wizard itself shoots a PWM frequency to that resistor box, right through the MOSFETs, just like our ESC does. And the resistor box puts a load on the battery. The battery voltage drops just like it does in an RC car, and we measure the current that goes through there along with the voltage drop, and it creates our internal resistance. All right, that is about all I have today, and this video lasted again longer than I wanted it to. I kind of go on, so I'm just going to cut this short, or cut this off now, and say thanks for watching. Have a good one.